Hi guys! Today we are going to be talking about Dalton's law of partial pressures and Graham's law of effusion. So first I'm going to talk to you and teach you about Dalton's law of partial pressures and show you how we're going to be using it in our lab. And then Ms. Frankovic is going to talk a little bit about Graham's law. So Dalton's law of partial pressures basically tells us that in a mixture of gases, each gas exerts part of the total pressure. Now, we've just been talking about the total pressure so far in everything that we've been doing, but now we're going to be able to figure out the partial pressure of each gas. So that's the part of the total pressure that each gas is responsible for exerting. This is translated into a formula that is very straightforward. It's our total pressure is equal to the partial pressure of each of the gases in that mixture. Now, we can use that also in moles. So our total number of moles is going to be equal to all the number of moles of each of the gases that make up our mixture. This is our little example. This is basically what our atmosphere is made up of: oxygen, nitrogen gas, argon, water vapor, and carbon dioxide. And all of these values down here are in kilopascals. And so in order to find the total pressure of our atmosphere, we are going to add up each of the partial pressures of each of the gases that make up our atmosphere. So if we have 20.9 kPa plus 78.1, etc., we are going to equal 101.3 kilopascals. That is our atmospheric air pressure. You can see that we label each of these by these little subscripts. So up here it just says P1, P2, P3, ... It can make up as many, those dots represent, meaning we can make up as many gases within our total. But down here you can see we label each of our gases as a little subscript. So the oxygen is going to be P with a little O2, P with an N2 for our partial pressure of nitrogen. Just a reminder that our gases are going to fill up the size of the container, like their volume is going to just be the size of the container because they're going to go up and take up that space. So we actually can't add together the partial volumes of a gas. That doesn't really work. And we can't add our temperatures together. The temperature is just going to be the same for each of our gases as the total mixture, due to kinetics. I don't know what else to say about that. So you can't add your volumes and temperatures together because volume always depends on the size of the container, and temperature is not going to change. It's going to be the same throughout the whole gaseous mixture. So our example of this is actually what we're going to do in our lab, and it is a sample of gas that is collected over water. It exerts a total pressure of 762 millimeters of mercury at 22.5 degrees Celsius. The vapor pressure of water at this temperature is 20.4 millimeters of mercury. What is the pressure of the dry gas? So the dry gas, we actually are saying, yeah, it's our partial pressure of butane gas. And where's the sheet? Okay. So although this is given to us in the only reason that the temperature is basically given to us in this problem is because it can tell us what the partial pressure of water vapor is at room temperature. And so we're going to measure the temperature in the lab, and then we are going to use this chart in the lab in order to figure out what the partial pressure would be.
These are standard. So this is a chart that I just printed off the internet. These are standard for every temperature, what the partial pressure of water vapor is there.
So for us, it was given, but that's where we found it on that little chart. And so you can see our partial pressure of water is actually equal to 20.4 millimeters of mercury. And our total atmospheric pressure at sea level is going to be 762 millimeters of mercury. So I'm going to say my atmospheric pressure is 762 millimeters of mercury. Oh, I was like, did I just do something wrong? Plus my partial pressure of butane, equals my partial pressure of butane plus my partial pressure of water. Now you're like, wait, how the heck did you figure out that those two add together to equal the 762? And I want to show you why. We are going to have water vapor. We're collecting, this is our little butane lighter, and you're collecting over water, you are collecting the butane gas inside this graduated cylinder. So we know that inside this graduated cylinder, the two gases that exist are butane and water vapor. So if we can see that adding those two together is going to be equal to our total pressure at sea level, basically. Is that a good enough explanation? So if I do my subtraction, my partial pressure of butane, remember I do big piece of butane is equal to 741.6 millimeters of mercury. But when I check my sig figs, I notice that my least known decimal place is actually my ones. So that is actually going around to 742 millimeters of mercury.
All right, so we're going to see one other type of problem when we're dealing with Dalton's law of partial pressures, and that is using it with our beloved ideal gas law, PV equals nRT, okay? So here's a problem that we've seen, a similar problem to what we've seen with the ideal gas law. The average lung capacity for a human adult is 6 liters of air. How many moles and grams, so we're looking for moles and grams, of oxygen would a big breath of air contain at room temperature and pressure? And I put in parentheses what room temperature and pressure is. It's the same pressure as STP, but the temperature is different. So at STP, our temperature is 0 degrees C. At room temperature, it's 25 degrees C. Okay, so we know a temperature over there, and we know a pressure. Now, what I underlined here is we're looking for moles and grams, but specifically of oxygen. Notice that this is talking about air in total, but my question is only about oxygen. That's where the partial pressure of oxygen is going to come in. So when we're looking for our variables, we're looking for pressure, volume, moles, our R constant, our gas law constant, and temperature. When we use this, we are going to have to use the partial pressure of oxygen, and we're going to be looking for the moles, specifically, of oxygen. Okay, so this is where Dalton's law comes in. So let's figure out our variables. Let me start with our R value. So, no, I should start with the partial pressure of oxygen. So we're talking about air, and I'm going to just bring us back to this board really quick. For our air problem here, we saw that the partial pressure of oxygen, not of air, but partial pressure of oxygen is 20.9 kPa.
This is just our normal, your average air that we're breathing in all the time.
So we have
20.9 kPa.
20.9 kPa is the partial pressure of just the oxygen in air. My R value, I'm in kPa, so we have to look at the back of the periodic table and find the R value for kPa, which is 8.31. My dog. Hey! Hey! And somebody's walking by right now. So, we know the partial pressure of oxygen. We know the volume. Now this is the same volume for all gases because all the gases in air will take up the same volume. The temperature is the same because all the gases in air are at the same temperature, right? So I've turned this into Kelvin, added 273.1, so I have 298 Kelvin. And what I'm looking for is the moles of oxygen. So I'm going to plug this into my equation. But remember that I'm looking for moles, so I'm going to rearrange this equation to solve for moles. So I'm going to have my moles of oxygen is equal to PV over RT. And this is pressure of oxygen. Without these O2s, it's the overall pressure and the overall moles. All right, so we are going to plug in our variables here. So we don't know N, and we're going to plug in our partial pressure of oxygen. So our partial pressure of oxygen
is 20.9
kPa.
Sorry, 20.9 kPa.
Our volume is 6 liters. Yeah. Divided by our R value, which is 8.31. We need the whole unit, so it's kPa times liter over mole times K. And then that is all multiplied by our T, our temperature, which is 298 K. Right, so if we solve for that, we get moles.
Remind us.
Oh yeah, our units cross out.
Make sure that
We're left with moles. And we get 0.0506 moles of oxygen. Okay? Now, we know how to quickly go from moles to grams. I'm going to set that up. Moles is going to go on the bottom, moles of O2. And it's 1 mole for 32 grams of oxygen. And we get 1.62 grams of oxygen, okay? So our question was asking for moles and grams of oxygen. The only difference here between what we've been doing with the ideal gas law and what we're doing now, again, is we're using the partial pressure and the partial moles of oxygen as opposed to the total of each, okay? So, let's take a look at our last gas law. This is Graham's law of effusion. Now, when we're talking about effusion, think about, I have 2 balloons up there, okay? So, if I have gases in those balloons, one balloon I have helium, one balloon I have argon gas. I don't know why you'd have argon gas in a balloon, but it just made sense for this example. We're looking at how fast these gases will go out of a small opening in the balloon. Okay, so effusion is movement of gas particles through a small opening in a container.
And I know it seems like extremely random, but it's important.
And typically we're talking about gases that are together in the same container. It would have been confusing to draw a balloon with 2 gases in it. So, we have helium and argon. Now, Graham's law of effusion says that the rate of gas A divided by the rate of gas B is equal to the square root of the molar mass of gas B over the molar mass of gas A. Notice the A is on top here, it's on bottom here. B is on bottom, B is on top. So they just flip-flop, they switch. We can also write it just like this. It's saying the same thing, the square root of the molar mass of B over the square root of molar mass of A. And I put in purple over there, M, capital M, not lowercase m, capital M is our molar mass. Now when we're looking at this, we have A and B. How do you know, if you're looking at 2 different gases, how do you know which one's A and which one's B? A is the smaller, faster gas. So think about like 2 people running. One like extremely small person or 2 dogs running. One extremely small dog.
Ella and Wally.
We should pick up
Wally.
Pick up Wally. So if we have Ella and Wally going for a run, oh gosh. Which dog do you think is going to run faster? Okay? The smaller dog or the bigger dog? Okay? Typically, the smaller dog is going to be faster.
Wally's not very fast.
So when we're talking about gas A, it's the smaller, faster gas. Gas B is the bigger gas that moves slower. It's Wally. The bigger gas is moving slower. Not to say
He's a little overweight. It's okay.
All right, so let's take a look at this example. We have equal amounts of helium and argon in a porous container, and they're allowed to escape. Which one will effuse faster and how much faster? And that's just asking for the rate. What rate of effusion is it? So I have to identify which gas is A and which is B. A is the smaller, faster one. So if we look over here at our molar masses, helium or argon, which one is smaller? Hopefully you're seeing helium. So A is helium.
We just know which one. We're saying smaller, and really the molar mass determines how big or small an atom is, right? So the one with the smaller molar mass is going to be a smaller atom, so it's going to be faster.
So the least massive.
Yeah.
Okay, so then B has to be argon, because argon is the larger or the more massive of the 2 gases. Okay, it's gonna take a lot more effort for that larger gas to get out of a small opening. So rate A, which is helium, rate of helium over the rate of argon is equal to the square root of the molar mass of argon. Okay, so B is argon, 39.95 grams per mole, divided by the rate of gas A, which is helium, 4.00. You should always have a larger number on top, okay? If you don't have a larger number on top, you've done it wrong, okay? So, square root of 39.95 divided by the square root of 4.00, and we get 3.16. All right? What does that mean? That's our rate of effusion. So, which of these 2 gases is going to effuse faster? Which one's smaller? It's going to effuse faster. Helium is smaller. So helium effuses 3.16 times faster than argon gas. All right? So that's what we're looking at when we're looking at the rate, right? Whichever one is smaller is the one that is effusing faster, and the rate that we get is how much faster.
You'll note that this has no units. This is like the one thing that we do that has no units because our unit cancels out. It's just talking about comparison rate of time. We're going to work on how you can solve for either one of the molar masses and identify the gas in class.